want to do today is I actually want to remind everyone. Oh, you're here, Tori. Here's your earbuds. I just figured out your name was on them last period. I first want to remind everybody that tomorrow is a lab makeup day, also known as if you have any missing assignments at all, you need to do at least one of them, probably more, okay? The next 2 Wednesdays, we will have a lab. So for those of you who are all caught up, you get a day off. If you're not all caught up, you don't deserve the day off because you took other days off that you shouldn't have. So tomorrow is a lab makeup day. Also, for my people at home, I want to remind you that today and tomorrow are the days to pick up the lab supplies for Thursday's lab. We're going to do a lab in person on Thursday. And if you requested supplies, they're available from 8:30 to 3:30 at the front office. No, I will provide everything you need in person. So we're going to do one lab in person so you guys can see, oh, labs aren't that hard. I should be doing them at home also. That's the goal. So anyway, we're doing that lab in person on Thursday. So putting our cell phones away, taking notes, Ainsley and Tori and everyone else who has their phones out are putting them away, so it's not a problem. Cool. So we're going to talk about reaction rates, and then we're going to talk about a different topic, which is energy changes and reactions. And so the notes we take the second half of today will literally help us get questions right on the lab. They'll help us earn points. So you don't need to write anything that's not in yellow. So the first thing here is not in yellow. It says in order for a reaction to happen, 2 atoms or molecules have to collide, and they have to do so with enough energy for the reaction to happen. And so in reality, there's collisions happening all the time, but they have to collide and they have to have enough energy in order for a reaction to happen. So when we look at factors that affect reaction rates, we're looking at factors that increase the likelihood of a collision, because the more collisions, the more likely we are that a reaction will go fast. I see a lot of noses out. Can we tuck our noses in, please? Just like they're going to bed and they're cold. So, factors that affect reaction rates. Number 1, temperature. If something has a higher temperature, it has more energy. And it's moving faster, so it's going to collide more. And those extra energetic collisions are going to cause more reactions. Did we notice that in the lab? Did anyone make it hot water and see it dissolve a lot faster? Yeah. Not just for dissolving, it's also for reactions. So increasing temperature gives them energy, more collisions, and therefore more reactions. Watching Zooms? Yes. If you haven't been watching classes that you've been missing, it's the time to do it. We're going to have our next test on May 13th, 9 days from now. May 13th. Yeah, like a 50-point test, like a test. Next thing that can affect reaction rates is stirring or agitation. Those are kind of the same thing. So when you stir something, you make it move faster, which means it collides more often and with more energy, so it can go it can react faster. So stirring it helps the reaction go faster. I'm thinking back to my days in the restaurant trying to make a lemonade out of lemon and sugar. Stir, stir, stir with my straw, and I can make a decent lemonade. Get that sugar to dissolve. So increasing the temperature speeds up a reaction. Stirring speeds up a reaction. Well, I did want to mention, I don't know if I remembered at the beginning of class, I assigned retakes for the covalent bonding quiz for those of you who asked for it or those of you who needed it. So those retakes went out at like 11 or so today, and you have until the end of the day Friday to work on them. We took it on the 29th of April, so I think that was last week on maybe Thursday. It was the one where we had to draw the covalent molecule and then answer questions about it. Most people either did quite well or not. There wasn't a lot of in between. Next thing that affects reaction rates is concentration, which refers to the amount of particles in a certain volume of liquid. The reaction rate is going to be faster if there's more particles, because more particles means more opportunities for collisions, and more collisions means faster rate. Are you sensing a pattern here? So if you have something that's very concentrated, that means there's a lot of stuff in it. If there's a lot of stuff in it, it can collide more often and react faster. There's two more factors that affect reaction rates. Anyone think they can guess one or both of them? Maybe you did one of these, not two. You couldn't have done the second one, but maybe you did one of them in your chemical reaction, in your experiment. What do you mean by volume? So that kind of falls under this category, concentration. So how much of it you have would kind of fall under this category. Did anyone crush their sugar? Like take the cube and crush it into a powder? Did it speed it up? Yeah. So the fourth one is particle size. Smaller particles means more surface area able to react. And you might not have thought of it like that, but think about it. If we put a sugar cube in water, which sugar can dissolve first? Just the outer layer, right? And then the next layer, and then the next layer, and then the next layer. If you powder it up, if you would like crush that sugar cube, then all of the sugar could dissolve at once. It could all touch the water at once. But if it was in a cube, it could only do one layer at a time was available to react. So particle size really can change the speed that something reacts. When it's in much smaller particles, when it's ground up into smaller pieces, a lot more of it is available to react at one time. And on the next slide, we're actually going to show a picture of a fire at a processing plant. And I hear about it in the news every single year since I started teaching chemistry. I've been aware of hearing about it. I probably heard about it forever and I wasn't aware. But basically every single year, despite all the safety processes, there will be a story, a little blurb in the news, at least once or twice a year, about a plant that makes flour or powdered sugar or regular sugar, but a processing plant where they're taking a food and they're grinding it into smaller amounts, where they will have a warehouse fire. Because if you were to take a bowl full of sugar and try to hold like a flame over it, it would just singe a little and get a little bit dark right on top, but it wouldn't really catch on fire. But if you took sugar and in the right concentration, you poofed it into the air and put that flame, it would literally burn. It's a very different experience because all of the sugar is powderized and in tiny little bits and it can all burn. Whereas when you're doing it for sugar in a bowl on top, you're just touching the very top layer. And so there's always stories of these grain elevators and things like that, where just the dust accumulates. There's some kind of spark from mechanical pieces, and it causes a huge fireball that basically rushes through the air. Now, they have tons of different processes in place to try to keep dust down and keep the product from aerosolizing. But when there's a failure in that system, when the fans aren't working right to keep it out and things like that, you will hear stories in the news every single year about fires that happen somewhere. Oftentimes now with the technology, people aren't in the space where that happens, so there aren't loss of life, which is very good. But this is because that aerosolized stuff is suspended in the air and it can catch on fire very easily because of particle size. This is the last one, and it is an important one, and it is not one that you would have done in your experiment. So this says catalyst/inhibitor, but I want to be clear, a catalyst is the opposite of an inhibitor. And so I defined the word catalyst, and then I defined the word inhibitor. So remember when we said that in order for something to react, it has to collide and have enough energy for the reaction to happen. A catalyst lowers the amount of energy needed during that collision for a reaction to take place. And a catalyst is really interesting because a catalyst allows a reaction to happen without getting used up itself. It's not part of the reaction, it just helps the reaction happen. And I used to work in restaurants. When I was in from like 15 on, I worked in restaurants as a hostess and then as a waitress. And my first job was at a kind of fancy restaurant as a hostess. And there were certain tables that were like particularly desirable and people wanted to sit there. And so when I think of a catalyst, I know it sounds cheesy, but I think of like the fancy romantic table at a restaurant. Because people go out, right? And maybe they could have had a good date, whatever they do. But if they go to this table, where it's really a great location and great food, they can have chemistry, bond, go on, and now that table is reset and another two people can come. They can have chemistry, bond, connect, go on, and then the table can be reset for someone else. That table is like the catalyst. It doesn't actually get used up, but it brings those two people or the two compounds together for the reaction to happen. An inhibitor is literally something that gets in the way of the catalyst so the catalyst can't do its job. So in restaurant speak, that's someone who comes to the table at 4:30 before the dinner rush with their book and stays there for 6 hours straight reading. So no one else can sit at that table. So all those couples that could have potentially come in and had these chemistry moments can't because someone else is sitting at the table. That's literally what a catalyst is and what an inhibitor is. So let's think about our bodies for a minute. One thing that your body probably does multiple times a day is digestion. Do you want your stomach actively digesting 24 hours a day? No, because you go for periods of time where you're not eating and the stomach acid would actually eat through your stomach if it were doing that. So you want your body to be able to turn on and turn off digestion, right? But when you do eat a big meal, you don't want your body to be going super slow in digestion either. That's actually really unhealthy for you. You need your body to be able to speed up the reaction of digestion. Well, the first thing we learned about is temperature. Is it a good idea for your body to say, you know what, I need to double the rate of this reaction. Let me double their temperature. Is that going to work in us? No. Just a few degrees of a fever can be really dangerous in humans. We can't dramatically increase our temperature to speed up the reaction. What about stirring? Can we stir our stomach? Not really. I guess jumping around on a trampoline afterwards might help or hurt, but can't really stir, right? Can your stomach say, you know what? I know you chewed a little, but that particle size wasn't quite right. Please try again. No, it kind of has to deal with what you gave it. I mean, it can reject the food, but you're probably not going to eat it again after that. Okay. So concentration, can your stomach say, you know what? You ate a lot of this, but could we have a little bit more of that? I mean, maybe it could. It's called cravings, but not really. Your body has to deal with the food you gave it and has to figure out how to digest it. And so the way it does that is with catalysts. We call them enzymes when they're in a living thing, but an enzyme is just the biology word for a catalyst, of something that speeds up a reaction. So here's an example. You all probably know someone who is lactose intolerant, right? Most people can digest lactose, not everybody can. Now, let's say you are about to have a big bowl of ice cream. If you're not lactose intolerant, then you're able to digest that. So what happens is you eat your big bowl of ice cream and your stomach goes, ooh, I detect lactose. And this is a very simplistic description, but imagine that like inside your stomach is like a locker room of all these different catalysts depending on what you eat. And your stomach says, ooh, I detect lactose. Let me open the lactose locker. And it releases the catalyst that digests lactose. And it does its job. And once all the lactose is gone, your body stores that catalyst again until it needs it. Now, if you are lactose intolerant, some people who are lactose intolerant can take a pill before they eat their big bowl of ice cream, and it will allow their body to digest the ice cream. But that's because their body doesn't make the catalyst. So the pill is the catalyst, so it can do the job. But since their body doesn't make it, their body doesn't store it, and then it just excretes that lactose catalyst. And they'll need to take a pill next time before their next big bowl of ice cream. But your body uses enzymes all the time to speed up different types of reactions, and then it stores those enzymes until it needs it again. And so catalysts are really what our body relies on to speed up reactions. So I don't want you to draw this, but I wanted you to look at this picture. So this is a reaction that shows energy on the y-axis and just time of reaction on the x-axis. And you see how we have reactants here, and then this big blue jump. That's the amount of energy the reactants need to actually react and turn into products. Now, if you have a catalyst, one thing it does is it reduces the amount of energy you need for that reaction to happen. So instead of this much energy, maybe you only need this much energy, and so the reaction is more likely to happen. All right, this is the second half of our notes, and now we're getting into the notes of information that will help you earn points on tomorrow's or Thursday's lab. So we're going to talk about chemical bonds and energy. So I think we even talked about last semester about how we have chemical energy, which is just energy stored in the chemical bonds of something. So when bonds are formed, they store energy. And it actually takes energy to break bonds. So like when your body takes in food, food is energy, right? Our body has to use energy to break up the food that we're eating. But then our body makes new compounds, and that releases energy that we can use. So like when you're breaking up a sugar molecule that you just ate, it uses energy to do that. But when you make carbon dioxide and water bonds, that releases more energy than you use to break up the sugar. If you ride bus 7, today you're riding bus 3, just for today. Thanks for hanging in there. This is literally the last notes for this test that's on May 13th, so you won't have as much writing between now and then. No, not quite. We got like 3 more. No, you're still hanging in there with me. It's a lot of talking today, but I'm not going to do so much the next few days. I like to be quieter.
What day is May 15th? Is it Wednesday?
No. May 13th is Thursday.
How many questions?
I just wrote it. I'm not sure if I'm done, but right now I think it has like 30 or 35.
So, more than the 24.
I guess so.
Oh, last one was 40. Oh, they are.
But they're always all worth 50 points. I weight them so they're all worth the same in the grade book. Or they're all like 49.95. They're all really close to 50 in the grade book. So each test is equal to every other test. Yes, I could. Would I? No.
Is it gonna be?
You give me the answer. It's going to be one day to do the test and then a makeup day where we'll watch Mythbusters if you're done early. And if you're not done early, you'll go in the hallway and I'll make you finish it. I don't think so. I guess we'll see. If everyone's going to be in the hallway, then we'll all just be in here. All right. So for chemical energy, energy is stored in chemical bonds. It takes energy to break a bond because think about it. Elements want to be bonded. That makes them stable, right? So you have to put some energy into breaking bonds, but then when new ones automatically form, that releases energy. And so everything is going to have a transfer of energy. Now, we have these 2 different types of reactions, and these are the 2 big vocabulary terms that you need to walk away knowing. And they are exothermic and endothermic reactions. Because you don't really need to write this, but it says during a chemical reaction, energy is either released or absorbed. You don't need to write this slide. The next 3 you need. But in order to describe the transfer of heat, we really need to describe what are we talking about. So we need to have a system and surroundings. So listen up. You're at a big bonfire. If the bonfire is a system, is it releasing heat or absorbing heat? Releasing. If you are the system standing near the bonfire, are you releasing heat or absorbing heat? Absorbing. So every time something is losing heat, something else is gaining heat. And so we always have to be thinking about, is it transferring in or is it transferring out? And that's where these 2 vocabulary words are going to be really important. Exothermic, this definitely needs to be written down and starred. An exothermic reaction is a reaction that releases heat to its surroundings. Heat exits the system. So in the case of that bonfire, the bonfire is exothermic. It's releasing heat into the environment around it. You can see here too, the reactants start out with more heat and the products have less because heat was released into the environment. It was given off. And then the other way would be endothermic. Yeah, also quite important. This is a reaction that absorbs energy from its surroundings. So we say heat enters the system. So that bonfire was exothermic. It was releasing heat into the world. And the world, or us standing near the bonfire, would be endothermic. Heat goes into us. So you can see the reactants here absorbing energy, and the products have more energy than the reactant started with because it has absorbed energy. So every single thing is either exothermic or endothermic. You're either absorbing heat or gaining heat. When you get in bed and your sheets feel cold, they're not cold, they're just not hot. And so it feels cold as heat is transferring out of your body into the sheets. And then once it stops transferring, then you don't feel cold anymore because you're not losing heat. So here's the thing, heat travels, cold doesn't. You can't get more cold, you can just get less hot. Cold is just the absence of heat. Heat travels, cold doesn't. So you either feel hot or less hot. Not cold. Out of your vocabulary. So imagine you have a drink that's not quite cold enough. Has that ever happened to you before? Okay, what do you do to make it a little bit colder? Put an ice cube in it. The ice isn't making your drink colder, it's making your drink less hot because the heat in your drink goes into the ice cube. So the ice cube is endothermic, it's getting warmer, and the drink is exothermic, it's getting less hot because it's giving its heat to the ice cube. So ice doesn't make it colder, it makes it less hot. It takes away that heat. It's always heat flowing, which is kind of weird to think about. So like if we have an instant cold pack or an instant hot pack, the way that you activate these is you like pop them or twist them, right? Because what it is it's a bag within a bag. So there's a solution inside the inner bag, and then there's something in the outer bag. And you pop it and you mix it, and a reaction happens. So in cold packs, it's usually ammonium nitrate and water. And when ammonium nitrate dissolves in water, it's an endothermic process. It absorbs heat from the environment. So let's say you twist your ankle and it's getting hot and swollen. You put a cold pack on it, and the cold pack absorbs the heat from your ankle. It doesn't make your ankle cold, it makes it less hot. So the cold pack is absorbing heat. It feels cold to your fingers because it's taking the heat from your fingers. Cool, because they don't want it to leak early. Same with hot packs though, but they're opposite, right? So iron and oxygen dissolving in there is an exothermic process. So when you activate a hot pack, it releases heat to the environment, so it feels hot to us because it's giving us more heat. So heat is either transferring in or out. If heat is transferring out of something, the environment gets hot. That's an exothermic process. If heat is transferring into something, the environment feels colder because its heat is being used up. That's an endothermic process. So on Thursday's lab, we're going to do 2 chemical reactions, and we're going to measure the temperature of the environment. And we're going to see the environment getting hotter in one of the instances and getting less hot in the other instance. This is our last slide, then we are done. So law of conservation of energy tells us that heat is not created or destroyed. It can be transferred from one thing to another. So the total energy before and after a reaction is exactly the same. It doesn't invent heat. It doesn't take, heat doesn't disappear. It just transfers from one thing to another. So my Zoomers, once you've gotten that down, we are done for today. Thanks for being patient with me. Tomorrow, if you have any missing assignments, do at least 1 or 2 of them, especially labs. And then I will see you on Thursday in Zoom where we will do a lab together. Make sure you pick up the supplies if you did not have yeast, baking soda, or hydrogen peroxide at home. I went a lot faster in this class period because I didn't have technical issues.